So today I'm going to be presenting some of my master's thesis work. So there are many notable people who have played a role in our present day understanding of cerebral blood flow regulation. As it pertains to caffeine and cerebral blood flow, it's still a relatively new area, but what we do know so far is that it reduces blood velocity and blood flow. But there's still some question as to how. While most studies suggest it's likely due to cerebral vasoconstriction via adenosine receptor inhibition, this leaves out a major factor. I'm sure I don't have to convince anybody in this room that the brain is highly sensitive to carbon dioxide. When you introduce caffeine into the system, it triggers an increase in ventilation, which in turn reduces end-tidal CO2 or PET CO2. So we can't be for certain that this inhibition is the only reason for caffeine's effects, which brings me to the purpose of our project, which was to investigate the effects of caffeine on cerebral blood flow and cerebrovascular function in regular coffee drinkers. So we first wanted to determine if these reductions post-caffeine are related to reductions in end-tidal CO2, and we hypothesized that controlling for this would eliminate the effects. And second, does caffeine affect cerebrovascular function in response to various stress tests? For today, I'll just be focusing on our hypercapnia test, and we hypothesized that caffeine would reduce middle and posterior cerebral artery as well as internal carotid artery reactivity to hypercapnia. So this is an overview of our protocol. For time's sake, I'll just focus on our baseline and CO2 step test. So we ran our study as a single-blind randomized design. We had a familiarization followed by a placebo, average, and double dose day. 14 healthy participants arrived to the lab in the morning fasted and restricted from caffeine. While preliminary ICA scans and the search for TCD signals were going, they were instrumented with ECG electrodes, a finger cuff, as well as a brachial blood pressure cuff. So first thing to note is that average caffeine intake of our sample resembled daily consumption, so these results are very relevant to everyday life. So as expected, we saw a decrease in MCA velocity and PCA velocity following both an average and double dose of caffeine, as well as a decrease in internal carotid artery blood flow during room air baseline. But this was associated with a drop in end-tidal CO2 following the average and double dose day. However, we successfully corrected for this using our dynamic end-tidal forcing system. Contrary to our hypothesis though, correcting for the change in CO2 or the drop in CO2 did not correct the decrease in blood velocity seen in the middle or posterior cerebral artery, and we still had a trend towards significance in ICA blood flow. This, however, did not affect middle or posterior cerebral artery reactivity to hypercapnia, as both were unchanged by caffeine. However, internal carotid artery reactivity to hypercapnia was blunted following both an average and double dose of caffeine. This did not translate to a change in ventilatory reactivity, which was unchanged across all dose days. So our major findings is that first, caffeine is a sufficiently potent sympathetic stimulant to reduce resting cerebral blood flow in intracranial arteries and in the internal carotid artery. Caffeine impairs reactivity to carbon dioxide in the internal carotid artery, but not the middle cerebral artery. From a research standpoint, this shows that there are some limitations to using TCD as your sole method to measure cerebral blood flow in caffeine research. And future work is needed to clarify the benefits and consequences of habitual caffeine consumption. So with that, thank you to everybody that assisted with data collection, our lab team and the collaborators, and thank you all for listening today.
Great presentation. Questions for Christabel? Ryan.
Ryan, UBC. Is there a relationship between how much caffeine people are using on a day-to-day basis and then the actual cerebral blood flow impact of your half or full dose?
They're resting or they're
Yeah,
changed?
so like if I drink more coffee than someone else, would the doses you use of caffeine have a bigger or a smaller effect? Is there an association there?
I didn't look at how their daily intake affected the magnitude of the change. I did look at how caffeine consumption related to resting cerebral blood flow. I don't have that. I was going to add it, but I forgot. And there was no correlation between daily caffeine consumption and resting cerebral blood flow. It was practically a straight line.
Okay, cool, thank you.
Go back.
Thanks very much for that. For your very last results with the internal carotid artery rates did not
So we did have some changes in ICA diameter. Let me see if I can pull it up here.
And I guess
It's somewhere.
Christabel is ready for 2 hours.
I don't know where it is. Somewhere. Where it is. Okay.
That is wildly
You're busy, I
impressive.
know, right? Dr. Timko, can you give us a yes or a no?
We did have a drop in diameter change. I just don't know if I have that slide. There was, but I don't have it.
And I guess with that, like, in your estimation, like, does that explain the difference between the ICA and the MCA, or?
So there's a couple of previous reasons that have been suggested. Let me pull back. So anatomical reasons could be that reactivity is just greater in the ICA. And then also technical reasons could be that there are diameter changes occurring in the MCA and PCA, but we just can't track that using a TCD. And with that, that could lead to some underestimation, which is why during the CO2 reactivity test, we didn't see a difference pre versus post caffeine. But I think the diameter could be a big factor, which is why we wanted to make sure that we did ICA and MCA PCA, because that was missing from a lot of past research. They would either do only MCA, very little caffeine papers even look at the PCA, or they would only do MRI. So we wanted to really make sure that we covered all bases.
Right, yeah, I agree. Again, I wonder if the MCA is doing the exact same thing, but you just can't see it. Thank you.
Final question, Jeff.
Thanks for that, it was phenomenal. Based on this research, can you make any recommendations for us as to what we're supposed to do with our participants and standardizing?
Yeah, so right now I lean towards you should test people in their native caffeinated state. Because when you do have them come in and they restrict from caffeine, yes, in a sense it's easier because you don't have to worry about any other confounding variables. That's why we also have them come in fasted, even though it really sucked for the participants because it was a long protocol, 3.5 hours. I think that testing somebody in their native state is the best representation of their everyday physiology, and that's what we should kind of lean towards. I have this conversation with Mike where when we're putting all these restrictions on people, yes, we might get cleaner data, but how much of a representation is that of what you see day to day?
Yeah, that's a great point. Tony, just.
Yeah, I was just gonna follow up on that with caffeine withdrawal. Remember we talked about,
Yeah.
you actually have an increase in brain blood flow. Right, so the question becomes, what is the
What is their
the true
normal?
resting?
Yeah, so when they are restricted, is that really their normal, or are they just in a state of withdrawal? So that was a big thing too. That would probably be the next step, to test people in their native state and to also include caffeine naive drinkers. Me being one of them, surprise, surprise, I know it's very ironic. I don't drink caffeine at all or coffee at all. So, so I think that would be a great thing to add on to this as well. I was hoping to get some caffeine naive people as well, but we just